Hello, this video is going to be about integrated time absolute error for a four-pole system, which happens to be equivalent to a hydraulic system in position mode. And at first what we need to do is calculate out the coefficients for the integrated time absolute error. To do that, what we need to do is write a fourth order differential equation. And what we want this to do is start at 0 or minimize the time it takes to get from 0 to a reference point, which is R, and R is assumed to be 1. So it's going to calculate these coefficients, these three coefficients, that will minimize the integrated time absolute error to get from 0 to 1. And in this case, what we're assuming is that A0 is always going to be equal to 1. I'm going to do this in 10 millisecond intervals, and they're going to have 60 seconds. So that's close to infinity, close enough. That's going to be 6,000 points. R is my reference. We're going to go from 0 to 1. This is the tolerance, and what it's going to do is it's going to iteratively try to calculate or find the minimum. We'll never get to a 0 error because you always start out with an error of 1. But one of the nice things about the integrated time absolute error is it doesn't count or weight the initial errors very highly as opposed to other forms like the integrated absolute error. So to start with, we have the initial conditions for the four differential equations or four states. So they're all 0, and it's going to go to 1. So what we have is, well, this is the first derivative, and it gets integrated to position, and then the second derivative gets integrated into velocity, and the third gets integrated into acceleration, and this gets integrated into jerk. So we got position, velocity, acceleration, and jerk. I'm going to use Runge-Kutta to numerically integrate this differential equation. And then this is the key to the integrated time absolute error. I'm going to run I from 0 to Z, which is 6,000. And this part is the absolute error. T is a weighting factor. It's not strictly necessary in this example because I'm just trying to do this minimization within this one program. But if I want to compare one integrated time absolute error with another one on a different program, you have to weight each one of these errors by the time interval that it represents. This I times T represents the time element, which is up here, this time element, and that's what makes this different from an integrated absolute error. So I'm going to assume some values for these coefficients to start with, and then it's going to do this iteration, and the error, the minimum error, is 4.59, and these are the coefficients that it works out. And you can see that I get slightly different answers depending upon well, round off errors, whatever. I don't know how it starts the initial conditions. So this is the Bode plot, and in this case, this would be the closed loop transfer function, and you can see that it looks very nice. But let me explain what this lambda is all about. If I just calculated these coefficients and it didn't include lambda, what would happen is we'd get a very slow response, and the frequency or bandwidth would be about 1 radian per second. And this is how you increase or decrease the bandwidth. So here I've got the bandwidth set to be about 10 hertz, which is 2 times pi times 10 radians. And this goes in the denominator for each power of s. So by making this a 10, I can get a frequency response of about 10. It's actually a little bit less because it's a 4-pole filter. If it was a 1-pole filter, then it would be exactly 10. So this is where the pole locations are. This calculates out the roots or eigenvalues or poles, and it plots them out. Now let me explain what lambda does to these poles. As I make lambda bigger or smaller, it moves the poles either farther away if I make it bigger or closer if I make it smaller. And then this pole would move out along this line, and this pole would move out back and forth here, and this pole would move out and back this way. So if I reduce lambda, all these poles would move in. Now we're going to see the time response. So what I have is the closed loop transfer function plus the step, that's R over S, and I'm going to plot that out. I'm going to do just a few iterations here. There's no need for me to do the whole 60 seconds worth because it only takes about 0.8 seconds to get in position. So you can see we're starting out at 0 and going to 1. And if I were to increase lambda, this would rise faster. And what you should note is that these errors here are not weighted very high, whereas these errors over here are weighted by how far we are from the time 0. And again, let's just print out the coefficients. So now I'm going to apply this to an actual motion control type application. And this is a model, idealized model for a hydraulic cylinder. This part here is the transfer function, the open loop transfer function for velocity mode. There's a gain, which has units of millimeters per second per percent control output. We have the natural frequency in radians per second. And this is the damping factor for the cylinder and load. And then with this extra S, we'll integrate velocity into position. Now, because this is a 4-pole system, we need to have 4 gains. So we have an integrator gain, proportional gain, derivative gain, and a second derivative gain. And in reality, this is very difficult to implement without getting a lot of noise introduced into your system. Now this is the closed loop transfer function. This part of my video is pretty much like some of the other ones I've done where I have this closed loop transfer function and I substitute the plant, which is a hydraulic system, the controller, into this equation and I get this and I simplify, and this is the simplified closed loop transfer function with the characteristic equation being here. For some reason I got the same thing twice. And what we're trying to do is we need to match the powers of S. So this is my desired closed or characteristic equation, DCE. And you can see I've got my 3 constants here. A0 is assumed to be 1, so I left it out. And what we need to do is match the coefficients for the powers of S. So this is the 0 power of S, and this has got to be equal to this. So this is my first equation. My second equation is matching this to this. Then I match this to this, and then this one to this one. So what I end up with is 4 equations and 4 unknowns. And if I solve the equations, let's see, let me just make that small and big again so it shows up properly. Okay. This is the equation for the integrator gain, the proportional gain, the derivative gain, and the second derivative gain. And there's a lower limit on how low the lambda can be because you can see if lambda is too small, this could be a negative value, which isn't a problem as long as you're not using gains in the forward path. The same thing happens here with the second derivative gain. Lambda can be too small, but usually it's the derivative gain that ends up going below 0 first. So if there's going to be a minimum lambda that you can use to make sure that derivative gain is going to be positive, so you can use the derivative gain in the forward path. Now, I'm going to compare this with a PID. Let me make this small and big again. Small and big. Okay, and basically it's matching the same coefficients as before. These are the same coefficients, but this is different because I no longer have the plus K2 term. So I only have the 2 times zeta omega term that you see up here. This term has gone away. Oops, slow updates. So I need to have 4 unknowns. I have a Ki, Kp, and Kd, but I also have to have an unknowns lambda. So what this does is it fixes lambda, and you can see that this is going to be very prone to having negative gains, because if zeta happens to be less than 0.52, that's the damping factor, the derivative gain is going to be negative. And that's a problem because most hydraulic systems are going to be damped at about 0.3 to 0.4, and sometimes much less. So the PID solution will not work for most applications that are using hydraulics. So now I'm going to do a motion control simulation, and I got a open loop gain of 10 millimeters per second per percent. So in theory, this model could go from 0 to 1 meter per second. Got a damping factor of 0.1. I could change this, but I just used 0.1. The damping factor, or the natural frequency of the system, is assumed to be 10 hertz. This is in radians, so it's about 62 radians per second. I have set the lambda to about 50 hertz. This is the time constant, open loop time constant. And some books would say, well, the minimum ramp time, according to many books, would be 0.95, but you can see in the example that we had above, we could probably do it in about 0.8 or 0.08 seconds. So using the PID, these are the gains I get. Because I used a damping factor of 0.1, you can see the derivative gain is negative, so that's not really usable. And then for the example with the PID with a second derivative gain, you can see that the lambda has to be greater than 34 radians per second, 34.58 radians per second. Otherwise, the derivative gain will be negative. But because I'm using a much higher frequency for lambda, I'm getting a much higher gains, and I don't have to worry about a negative derivative gain. This is the formulas for calculating out feed forwards. You can look at some of my other videos to see how I calculate those. And then for testing robustness, what I like to do is, now that I've calculated out the feed forwards and the closed loop gains, assuming that I know the ideal model of the system, I like to vary the model of the system a little bit to simulate the fact that the model could change over time due to temperature or loads or whatever. And I like to see how robust my control is. So I assumed that originally this was 10, and now it's 9.5. I assume this is 0.1, now it's 0.905, and this is assumed to be 10 or 62 radians per second, and now it's 0.59. And I'm doing the motion with the feed forwards. I'm calculating out the jerks and using Runga Kata to integrate this. So what I get is an array of times, position, velocity, acceleration, and my PID output. So I'm using a fifth order target generator, and you can see that even though the parameters have changed, in other words, this should have been 10 and it's really 9.5, you can see the control is actually very, very good. And what I normally would do is I'd run this through many iterations to make sure that the control is good. This is the velocity and acceleration. And let's see, these are more calculations, which, see, this is the Bode plot calculation. Now, what's different here is that I'm using zeros in this. You can see up here, I've got the, if I just had Ki in the numerator, then it would have no zeros. But since I have all the gains in the forward path, remember this is the forward path, this is the backwards or the feedback path. Each one of these, well, there's the number of zeros is going to be equal to the number of gains divided by, or minus 1. So there's 3 zeros and 4 poles. And the zeros extend bandwidth. You can see that even though I had the bandwidth set for 10 hertz, this actually extended the bandwidth out beyond, well, to about 20 hertz. But the downside of that is that you have this little bump here in gains. This can be eliminated by placing the zeros too. So you can see the bandwidth is actually almost 25 hertz. So now I'm going to plot the poles and zeros. And you can see the poles and zeros. The poles have the same pattern as before. You can see the zeros are about at the same frequency as the poles. And that's what's causing, the zeros cause the gain to increase and the phase to increase. And you can see that's happening here at 10 hertz. If I didn't have the zeros, then this would just kind of go down like this, like it did in the original Bode plot up above. I know I went very quickly. If you have any questions, you can ask them in the comments. If I went too fast, you can always slow this down or replay. I hope you enjoy the video. That's it. Goodbye.